Good afternoon, everyone, and welcome. My name is Tori Weston, and today I'm going to be presenting my electromechanical heat treating oven that I designed and created for my senior project. So things I'm going to be talking about: acknowledgements, purpose, the process, system level diagram, calculations, the controller, the heat treating oven, specifications, the testing process, my Gantt chart, a bill of materials, project tasks, and I will host a Q&A session at the end of this presentation. So at this point, I would like to recognize individuals and organizations who helped me throughout this project. So up first is Capital Steel and Supply Co., Professor Michael Marceau, Professor John Kidder, Barry Woodworth, LabTech Peter Cassavan, Gary Shores, fellow classmates of ELM 4702, and finally, my family. So many of you are probably wondering, first of all, what is a heat treating oven? Second of all, what is the purpose of heat treatment? So a heat treating oven is exactly as the name implies. It's an oven designed to heat treat, in my case, ferrous materials. Now the purpose of heat treating is to alter the physical properties of a material to extract different characteristics, such as hardness, strength, toughness, ductility, and elasticity. All of these characteristics can be tailored to the application. So the process of heat treating a ferrous material generally involves 5 different phases. The first phase is a preheat phase, which is characterized by controlled low heat. The second phase is the austenitized phase, which is characterized by high heat. The third phase is quenching in an oil, water, or gas medium to rapidly cool the material. The fourth phase is tempering. This is done at medium heat, and this reduces the overall hardness of the material. Finally, the fifth phase is a cryogenic quench, which could be in a liquid nitrogen bath. It further refines the grain structure of the steel. So this is my system level diagram, and its purpose is to provide a graphical overview of all major components within my project and how they interact. So here I'm powering the oven through use of a 240 volt power supply. That signal is sent through a relay switch, solid state relay, which is nothing more than a switch. When I apply a small DC signal at the input terminal of the relay, a contact between the 240 volt power supply and the Canthal heating elements is made. So the purpose of the Canthal heating elements is to dissipate the 240 volt power in the form of heat. These elements are responsible for heating the inside chamber of my oven. Now, the oven body and frame are made of special insulated fire brick. These bricks are designed to handle very high temperatures and possess a very high R value. Surrounding the oven body is a ceramic blanket which aids in further insulating the oven, and it prevents wear on the bricks from contact and the metal frame. Embedded within the oven is a Type K thermocouple. Now the purpose of the thermocouple is to relay temperature information inside the oven to my controller device. Now, a thermocouple is made up of 2 dissimilar materials formed at a junction. Now, a thermocouple operates on the Seebeck effect, which states that as the temperature of this junction increases, an electromotive force proportional to the inside temperature of the oven is produced. So, the output from the thermocouple is fed into the AD595 IC chip. Now the purpose of this chip is to convert the signal from the thermocouple into a scaled temperature and voltage signal. In this case, the output is scaled at 10 millivolts per degree centigrade. The National Instruments MyRIO works in conjunction with a National Instruments LabVIEW program to operate as a controller. So here, the MyRIO device is acquiring the signal from the AD595. This signal is being converted to a temperature internal within my program to a temperature in Fahrenheit. The controller is then making decisions to turn on or off the solid state relay, thus regulating the internal temperature of the oven. So as engineers, we like to ensure that the project is going to succeed from the start. So to do that, we start out with an idea. We then calculate, we simulate, we build, and then we test. In my case, I was not able to simulate the heat treating oven, but I did perform a number of calculations related to the heating elements to ensure that the oven would come up to temperature and the elements would not burn out. So as I stated earlier, the National Instruments MyRIA works in conjunction with a National Instruments LabVIEW program to function as the controller. Now, as part of any LabVIEW program, there are two elements. The first is the front panel, the second is the block diagram. So this is the front panel of my LabVIEW program. This contains all of user inputs and acts as a user interface. Here I set the temperature, I can set the hysteresis range. The set temperature and actual temperature are displayed here in these numeric indicators. And I can monitor the ramp speed and times of the temperature in the oven. Down here is emergency stop in case you need to perform a controlled shutdown of the system. This is the block diagram of my LabVIEW program. Now, the code on the left-hand side is responsible for first acquiring the signal from the AD595 and converting it to temperature Fahrenheit. That signal passed into a loop within my main loop that effectively acts as a hysteresis controller. This controller is responsible for turning on or off solid state relay, thus controlling the temperature into the oven. So our semester's worth of work, I'd like to present a heat treatment. So some of the main features of the oven include the aluminum shroud angle iron frame. The door operates on a hinged mechanism and uses a counter to stay open as well as closed. Inside the oven, thermocouple and menthol heatings. When the door up, this mechanism disables power to the system, enables power to the system. When it prevents power from flowing to elements to a shock. The RIO device and a circuitry that acts as a controller. Here I'm a solid state relay. At the rear is the master switch and square it leads to exit the oven. So, the chamber size is 4.5 by 15, operates at 40 volts, it draws 12.5. The elements dissipate 3 watts, uses a standard means 20. The matter is 2,000 degrees Fahrenheit, and your accuracy guaranteed at degrees Fahrenheit. Considering this a heat treat, I felt the best way would be heat treat an actual piece of steel. So the process included data sheets, heating at a critical temperature, in water, tempering 500s, and testing sample height. So the purpose of this will be compare the hardness of the material to the toughness. So this is chart describes heat or P95 carbons. Now here on the left, the temperature is 500. Let's reference that outside of the chart with the raw wood. So what they're saying is for the P's at 5 is the furnace should be
2 hours at 3, so the peak total of hours. And here's a thermal gun. The temp of the piece inside the oven is 500, which is very expected. 500. The first step processing the sample harm, forming a rest. These switches are here. Notice on the scale the rock setting. And 50, 50, 50. Needle indicates the piece was 57 rock. All testers in all trials push the same. I crushed the rock Brunel test. The measure to the measure, and it was the type in Stockwell. So